we're covering integration by trigonometric substitution. And as the title suggests, what we're doing is we're going to use a substitution when we are integrating, but that substitution is now going to involve a trigonometric function like sine, tangent, secant. So if an integral contains any of the following expressions, and I'll indicate what those expressions are, there's basically three cases to consider. Then I want you to consider using a trigonometric substitution, and I'll go through the rules for each of these three cases. The different trigonometric substitutions are provided below. So again, those three cases. Each substitution is based on a corresponding trigonometric identity. And I think understanding the trigonometric identity is really important if you don't want to memorize the different cases. Just understand the trigonometric identities, and then you won't have to memorize these three cases, which I'm going to show you. Also, the restriction on theta is imposed to ensure that the function that defines the substitution is one-to-one. So basically, when I go through each of these three cases, you're going to have a restriction on this new variable theta. We are using trigonometric functions. So there's going to be a restriction on this new variable you're introducing. And just understand that we need that restriction there because trigonometric functions are not one-to-one. Okay, so we want to restrict these trig functions to make them one-to-one in the substitution that we are using. So let's go for the first case, and that is case 1. So case 1 is where you have an expression of this form. Now let me just go through it. You have the square root of a squared. Now a is a constant number. All right, so you'll have a squared, and just note you won't always have some number squared like 3 squared, or you won't have 2 squared, for example. You may have 9. You need to recognize that 9 is 3 squared. Okay, you can write 9 in that form. In that case, your a would be 3. What if I have 10 minus, let's say I had 10 minus, and let's complete that expression, 10 minus x squared. Well, now there's no perfect square. Okay, what are we going to do? Well, that's no problem. We just need to recognize that we can take a to be root 10 because root 10 squared is 10. Okay, so you don't need to have a perfect square, and you don't always need to have some number that is going to be squared. You just need to have a constant, and then you can obviously write it in that form, a squared. So the first case is where we have something of this form, the square root of a squared minus x squared. The substitution that you need to use, and this is a general case, okay, is x is equal to a sine of theta, where theta is an element from negative pi over 2 to positive pi over 2, and it is inclusive of those two bounds. Right, remember, this is what I was talking about, that restriction on theta. It just makes this function here, the substitution basically, 1-to-1. All right, now why x is equal to a sine theta? Why do we need to use that? Well, the identity that this substitution in case 1 is based on is 1 minus sine squared theta is equal to cosine squared theta. So let's say I ask you to integrate this, and in the next example we are going to integrate this, but let's just say I ask you to integrate this. And right now, using the methods that you've learned, if you haven't learned trigonometric substitution, it might be a bit challenging or difficult. But here's where this identity comes into play. What we're going to do is we're going to let x equal to a sine theta. So our integral will become a squared. We're not going to touch that. That's a constant. Minus, now wherever I see x, I'm going to replace it with my substitution, which is a sine theta. Okay, a sine theta. And the squared is on the outside there. Let's simplify this. So we'll get a squared minus, and then we take the a to the power 2 and sine theta to the power 2. So we'll get a squared sine squared theta. All right. And then what we can do is take out a common factor of a squared. So it'll become a squared into 1 minus sine squared theta. Hopefully you can see where this is going by now. And we have the square root of a product. So that's basically the product of square roots. That's a fancy way of saying I'll take the square root of a squared separately and then multiply that by the square root of 1 minus sine squared theta. And the square root of a squared, that's just a. And then 1 minus sine squared theta, well, there's the identity. That's where this entire case 1 came from. It's from the identity 1 minus sine squared theta is equal to cosine squared theta. Then we have the square root of cosine squared theta here, and that's just a cosine theta. So this is what I want you to, so I don't want you to go through that entire derivation. I'm just showing you that so you remember where that identity came from. I'm showing you it's not magic. This is how I want you to remember it. Think of this constant number. Don't think of it as a squared. Just think of it as 1. All right, just pretend it's 1. So you right now have 1 minus x squared. Okay, now you know you are going to replace x. That's why it's called substitution. You have to replace x. So you want 1 minus what squared basically, and that should simplify to another trigonometric ratio. You know that the identity 1 minus sine squared theta is equal to cosine squared theta. So this x should be something involving sine theta because you're going to square it anyway. And then once you have that, it's pretty easy to work out what your a needs to be. And I'll go through a couple of these examples to show you how to work out a. It's not difficult at all. Why I'm telling you, or I'm emphasizing the identities, is because there are other identities that you can use. Again, there's 3 cases. So there's 3 choices you have for your trigonometric substitution in general. All right, so this is the first one. It's based on 1 minus sine squared theta is equal to cosine squared theta. Let's see how this works in an example. All right, exercise 1. Solve the following indefinite integral using a suitable trigonometric substitution. Now I'll go through this one with you. If you want to try it on your own, pause the video now and try it. Okay, let's do this. So I gave you a hint for this one. When making the substitution, do not forget to change dx. All right, so you're going to transform this dx into your new something involving your new substitution variable. In this case, it'll be theta. I'll show you how. And also remember that once you arrive at your final answer, you need to return to the original variable x because that's what the question was in terms of x, not whatever variable you introduced. So let's go for this example. So easy example because we just covered case 1. You can see this is case 1, but I don't remember the cases. I just remember the form of the integral. I see here that I have a squared. Let's treat that as 1. I know I'm using a trigonometric substitution, so it's basically 1 minus x squared. Think about what trigonometric identity has 1 minus something squared, and that's going to give you another trig function. That is, the identity is 1 minus sine squared, and that's equal to cosine squared. Obviously, there's a theta here. I'm just writing out the trig functions. So we need to be using this one here. If you memorize it, it's case 1. So this is what we're going to do. It's of the form 1 minus sine squared theta. I'm going to make the substitution x is equal to a sine theta. Now, why am I writing out a here? Let's think this through. Let's not memorize, let's think this through. I have x squared, so I'm going to be squaring this term here. I know, let's do this mentally, I'm going to get a squared times sine squared theta. That a squared is going to match with that a squared in the front. I can pull it out as a common factor and take the square root of that a squared. Okay, it won't always be this simple. That's why I'm teaching you how to recognize what the substitution is. So x is equal to a sine theta. Next, we also need to get dx. So dx, d theta. So we're going to differentiate that with respect to theta. Simple stuff, that's equal to a cosine theta. This means that dx is equal to a cosine theta multiplied by d theta. There we go. All right, so we have that. Now let's put this in my integral. So I'll go through this in detail. We're going to have the integral of the square root of a squared is a constant. Let's not touch that. Minus x squared. So we have x squared. I'm going to replace the x with my substitution. That's going to be a sine theta, and that's going to be all squared. There we go. Right, and we take the square root of that. And then I need to replace dx. So dx is going to be a cosine theta d theta. So it's going to be a cosine theta d theta. Right, we've done our substitution. Everything is now in terms of our new variable theta. Let's simplify. So we're going to have the integral of square root. Again, we'll get a squared minus, let's square that out, a squared sine squared theta. What I'm going to do in this line as well, I'm going to pull out a common factor of a. So I'll get a squared into 1 minus sine squared theta, close the bracket, multiplied by see that a there? It's not a variable, it's a constant. And like I always say, let's take the constants out of that integral. So I'm going to take the constant out and put it in front of the integral. It's just going to be multiplied by cosine theta d theta. Let's work with that in front. So we'll have the a multiplied by the integral of, we're going to have the square root of a squared multiplied by the square root of 1 minus sine squared theta. Let's work with this now. The square root of a squared, that's just a. Okay, so that's just a. Notice how I have a constant or coefficient in this integral. Let's take that out of the integral and put it in front. It'll be a times a, and that will give me a squared. All right, and under here, we have 1 minus sine squared theta. That is going to change to cosine squared theta. But look at how I have the square root of the cosine squared of theta. So the square root and square sign cancel off. What I will have is just cosine theta multiplied by cosine theta d theta. Now cosine theta times cosine theta, that's just cosine squared theta and d theta. And look at this integral that we now have. We have to integrate this. This is just one of the standard trigonometric integrals that we worked with in previous lessons. We have to integrate this, which is much easier than trying to integrate that without a trigonometric substitution. So let's complete this integral. Cosine squared theta, we're going to use a trigonometric identity. So we're going to have a squared, that's the constant of the integral of cosine squared theta. It is equal to half of cosine 2 theta plus 1. That's a trigonometric identity, right? It's based on double angle formula. Now notice how we have a constant here. That's half. Again, let's take it out. A squared over half. And now I have to integrate that. So let us integrate it. So it's going to be a squared over 2 into the integral of that. That is going to be half sine 2 theta plus integrate 1 with respect to theta. That is just going to be theta. Right? And then it's an indefinite integral. Let's not forget the plus c. Now, are we done with this question? Okay, take a minute and think about it. Yes, we've done the integration, but our answer is still in terms of theta. Right? Our answer is still in terms of theta. What we need to do is get it in terms of x. So let's just simplify this. We have a squared over 4 multiplied by sine 2 theta plus a squared over 2 theta plus c. We need to transform these thetas into, we must basically remove them and have only terms involving x. How are we going to do that? We are going to use, obviously, the substitution that we used in the beginning. So the substitution that we had was x is equal to a sine theta. We're going to use a bit of basic trig now. So x is equal to a sine theta, and we need to use the substitution to replace the thetas there. Okay, how are we going to do this? So we can solve for theta. We can have sine theta is equal to x over a, and theta is equal to, I'm going to have arc sine. So this is not sine to the power minus 1, it's arc sine. That's going to be arc sine of x over a. There's theta solved for, so we can get rid of that. Okay, now we need to deal with sine of 2 theta. How are we going to work with that? So recognize that, let's get this out of the way first. Let's just get that there. Okay, take a look at that. We can create a right angle triangle and fill in these values on the sides of the triangle. So what I mean by that is we can have a right angle triangle here. That will be theta. Sine theta is opposite over hypotenuse. So opposite over hypotenuse, that's x over a. So x is the opposite, hypotenuse is a, and the remaining side, the adjacent, must be the square root of a squared minus x squared, theorem of Pythagoras. We have sine 2 theta. There's a bit of a problem. Our angle is theta, but we have sine of 2 theta. We are going to use another trigonometric identity. So sine of 2 theta, sine of 2 theta, that can become 2 sine theta cosine theta, again your double angle formulae. So it's now 2 sine of theta multiplied by cosine theta, and we can get sine theta and cosine theta from our triangle. Well, sine theta we can technically get from our substitution, but the cosine theta can't really get it from the substitution in that form. You have to get it from the triangle. Now we can complete this question. So let's get that out of the way. What we are going to find out is we have a squared multiplied by 2 sine theta cosine theta. Let's simplify that. That is going to become a squared over 2. Okay, and then plus a squared 2 theta plus c. Okay, so it'll be a squared over 2 sine theta, that's x over a, so multiplied by x over a, cosine theta, that's adjacent over hypotenuse, adjacent over hypotenuse. So that is going to be a squared minus x squared over a, and then we will have plus a squared over 2, and what did we have for theta? We had arc sine of x over a, and then we're going to have the plus c at the end. Plus c. Let's just simplify this. So we have a squared multiplied by a multiplied by a. That is going to cancel off. So the a's cancel off. We'll have x into square root of a squared minus, why am I writing plus? Minus x squared over 2 plus a squared over 2 into arc sine of x over a plus c. And that's your final answer. That is how you handle this trigonometric substitution for the integral.